Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Everyone, it's a great pleasure to welcome Will Evans from the University of British Columbia. Will got his PhD from UC Berkeley and is a friend of many of us who went to school there. And he was an assistant professor at the University of Arizona, where he made some great connections. And more recently at the University of British Columbia, he works in computational complexity, specifically looking at code compression and cloning. And today he's going to talk about his work on code cloning.
Thanks very much. Thanks, Ben. And thank you all for coming in. Thanks for having me here. It's a pleasure to give a talk about this material. I should give you a disclaimer at the beginning. I'm a theoretician, so I'm interested in the sort of theoretical questions that arise in this work, as well as the practical applications of it. But you'll see that sort of I'm a little heavy on the algorithm side as we get going. This talk is about clone detection. And clone detection via what we call a structural abstraction, which is using abstract syntax trees. It's joint work with Fraser and Fei Ma, who are both here, which is sort of amazing because I don't think we've ever been in a room together before. Fei was a student at UBC when we were doing this work. Chris, I think, was at Microsoft when we started doing this, and then went on to Google, and now is leading a life of luxury. And in any case, let me tell you what this is about. So first of all, clones. Oh, and so clones they're duplicated fragments of code. And the thing about clones is they can occur at many different levels. They can occur at the source code level. And these are typically sort of the copy-paste type programming clones. Like somebody copies a piece of code and they copy and paste it down and then modify it to do what they want to do. But they can also occur at lower levels, like at the bytecode or at the machine code level, because of perhaps idioms that aren't introduced by the writer of the source code, but by the compiler itself. And so these clones or copies of bits of code at the source code level, there's desire to detect them or to eliminate them for software maintenance reasons. At the lower level, there's reasons for that are in addition because of a reduction in code size that you want to perform. So if you find that your compiler is, for instance, inserting the same sort of code as a header for each of your modules, then having that header information being abstracted out into a sort of a common place is a way to reduce code size. But for this talk, I'm going to mostly stay up in the source code level. And when we're talking about source code clones, the real problem with those is a software maintenance issue. That is, if you copy a piece of code and use it for yourself, and later on the person that originally wrote the copy goes and says, oops, I had a bug, and they change their original copy, and you don't know about it, then your copy has this bug that's carried around throughout the code. And so automatically detecting these clones is a way to ensure software quality. And one of the other reasons to do it is because of a desire for comprehension of the program. So in this case, if you have two copies of some code, then ideally what you'd like to do is abstract the commonalities between those two copies into a procedure which captures the similarities between the two and exposes the differences between the two as parameters. And the reason you might want to do this is because, well, first of all, it's easier to see the differences if they're highlighted as parameters to a common function. And secondly, the procedural abstraction, the process of taking some piece of code that's common among many different places and putting it in one procedure, that process is a good way of organizing the code. It's more structural programming, so it aids in the comprehension of the software. My original interest in this came from trying to reduce code size. So I was interested in finding copies of code fragments to basically reduce the size of executables that were intended to be executed on limited memory platforms. So for instance, think about executing for instance, Microsoft Word on your cell phone, the executable is pretty big. It's not the data that it's using, it's not the data structures, but the executable itself that might be too big, and you want to find commonalities in that code to sort of scrunch it down and make it executable. This is one technique for doing it, this procedural abstraction. But there's another reason, which is sort of becoming more prevalent today, which is for transmission of code. And JavaScript that's flying around on the internet is flying around in a form that could be more succinct. And so that's essentially another motivation for looking at it. So here's one slide of background. There's a huge amount of work that's been done in this area. And I want to focus on just the sort of clone detection literature. There's also code compaction and code compression literature, but this slide is entirely about clone detection, so mostly from the purposes of software maintenance. So originally, the idea was, because this is copy-paste programming, the syntactic or token-based, textual-based methods were the initial ones to be used in finding these clones. So the difference between, for instance, this and like just string matching is that the procedures or the commonality that you're looking for can have slight differences. And so you, for example, want to handle variable renaming. And Brenda Baker did this in '95 using a very clever modification of the original source, which allowed for a suffix tree-based approach, but permitted variable names to be renamed as long as they maintain consistency. So here you see A and A, C and C. Those changes, A to C, were made sort of in parallel. They're occupying the same positions in both cases. There's sort of extended work on that called CC Finder by Kamiya, who runs a normalization phase at the beginning to do it, and then runs a suffix tree textual-based. These are token-based, textual-based methods. There are also methods based on feature vectors. You take features of a function, you create a vector in some unbelievably high-dimensional space, you cluster those, oddly enough, using the Euclidean distance for your clustering, which is interesting, and then you examine those clusters to see if there are clones within them. There's also techniques using abstract syntax trees. That's what this talk is about as well. There's an original paper in '98 by Baxter, which was describing a technique that I'll explain a little bit more detail on the next slide for handling basically limited pattern finding within abstract syntax trees. And there's another paper, more recent paper, which linearized this tree, basically wrote it out in pre-order, and then applied token textual-based methods. These original reasons for going to abstract syntax trees over tokens and textual-based methods was because some of the clones that were being found in the textual methods were violating program boundaries. So you would find a clone, for instance, that spanned a function boundary, and it wasn't actionable. You couldn't abstract that procedure. By the way, I don't think I mentioned this, but I think this talk is really short, at least I hope, which means that there's lots of time for questions if you have questions about things. Yeah.
So is there a notion of sort of the granularity of the clone that you want to find in terms of the size? I mean, obviously, a single expression, a single sub-expression might be too small, right?
Yeah, it depends actually on the Oh, sorry. Thank you for reminding me. So the question was, is there a granularity to these clones? Is there some small, like for instance, you want to not detect clones that are only one line long, or some limit on how small they should be? And really it depends on the application. For the purposes of software engineering, you want to look for big clones. You want to look for things that are reasonable size, and so people typically will look for things that are at least 5 lines or something like that, maybe even more. But for compression purposes or compaction purposes, often what you'll find is the tiny ones are the ones that give you the best bang for the buck. You get a zillion copies of something where you can save a little bit on each copy, and it's a big win. So it really depends on your application. And that's especially true when you're talking about sort of these automatic compaction methods. So the ones that you're producing something that no one's ever going to read. So it doesn't really matter how small the clones are that you're finding as long as they're providing you some sort of benefit. There are other methods as well, many other methods. Some involve data mining in the basic blocks. So you basically look for patterns, sequences, subsequences of common basic blocks that occur. There's program dependency graph type techniques that use program slicing to look at how code that's sort of using structures in a common way and looking for patterns that way. But we're going to be interested in this one. That's why the yellow stars are abstract syntax trees. So this is an abstract syntax tree. It's a tree. It's expressing some sort of a operation a plus b minus 7. And I can represent this as a tree. I'm also going to be representing it as this sort of parenthesized expression. This is a textual representation, but again, you really should think about it as being a tree structure. It's not, I'm not doing pattern matching on this text. I'm just thinking about it as being a way of succinctly representing a tree. Okay, and so what does a clone look like? Well, here's a clone. There's two occurrences of the same tree, except in this tree we have a constant 3, and in that tree we have the local variable a. And so those two trees are the same except for a single parameter or a single location, a single full subtree in terms of the tree. That is, a full subtree is a node and all of its descendants. So these two full subtrees are common between the two, are different between the two, and so I can abstract that out as a parameter, and it shows up as what I'm going to be calling a hole in my pattern. This is a pattern now that matches that tree and that tree. So you would think of this as being perhaps a subtree of a very large abstract syntax tree, and maybe that's another subtree. This pattern would match those two occurrences. Okay. The hole in this case is something that I would view as being a lexical or textual hole, meaning that the only difference between these two is really something that a lexical analyzer, token-based system, would be able to abstract out. So, for instance, Brenda Baker or the CC Finder stuff, they would be able to normalize that away by perhaps replacing all local variables and all constants by wildcards and then doing a textual-based method. So this I'm viewing as being a lexical clone, and if I was only looking for lexical clones, I would probably be using some sort of syntactic-based method. But I'm not. I'm looking for structural clones, which is what this talk is about, is to try to figure out if more complicated parameters like this, which is an actual operation, C plus D is actual little subtree that's more complicated than just a lexical, a single lexical token, whether those are common or not. That's a parameter that's more than just a constant or a local variable. Again, the same pattern would match, but now this pattern is a structural clone. I'm equating clone here with pattern. The pattern is representing the clone is represented by the pattern. And this clone now is a structural clone because it's taking not only these lexical parameters, but also a more structural parameter. So the big question is, well, so what? I mean, how often does this happen? Maybe never, right? Maybe they're all supposed to be. Maybe they all turned out that they're all these sort of lexical clones. We were interested in trying to figure out whether structural clones are something that's prevalent and how to find them efficiently in big programs. Okay. So this is backing up a little bit in history. So this is Baxter's approach to finding clones within an abstract syntax tree was to hash full subtrees of the abstract syntax tree. So you take these big full subtrees, you'd hash them into buckets, and you basically cover up the local identifiers down at the leaves so that those weren't part of the hash function. So you'd hash their sort of skeleton structures, and then you'd go look inside of a bucket and see if you could find two subtrees that matched. If you did, then you found a clone, and if you found a clone, then you tried to improve it by climbing up. You try to find a parent that would have two children or more children who were already matching clones. And if you did, then you'd say, oh, good, now I have a bigger clone by climbing up. So I'm going from my I'm going to my parent. The problem is that if you start with something where there's a difference in, for instance, something that might be a parameter. So you have one big subtree that could be a parameter of a clone and another small subtree that could be the other parameter, then, well, you won't find that using this technique because the original bottom part of the clone doesn't match. So it doesn't have anything to grow from. It can't go up. So, of course, what do? Well, you say you shouldn't grow up, you should grow down. And that's the approach that we took in Asta, which is you try to grow clones down. So you start off with little teeny-weeny subtrees, not full subtrees, just little teeny-weeny snippets, and you try to grow them down. So initially, we start with what are called the 1 caps, 2 caps, 3 caps. These are patterns that are formed at a particular node, like this node V, by slicing off everything that's below a certain level. So the 1 caps, you slice everything below at level 1, and you replace that with parameters, so 2 question mark parameters, 2 holes. So you get this pattern. That's the 1 cap. The 2 cap is you slice at level 2, the 3 cap you slice at level 3, and you get a sequence of patterns here until you got to the full cap, which is the entire subtree rooted at the node V. And so the first step of Asta is just to find all the D caps for everything, for D ranging from 1 to, let's say, 10. And you stuff all of that into a hash table. And essentially, you create an associative array indexed by these patterns, by these caps. OK, so that's the initial part. Then you try to make things better by growing down. So you start with pi, the set of all D caps and full caps. And then for every pattern in that set, you try to improve it in a way that keeps all of its occurrences. So every pattern has a set of occurrences where it shows up inside of the abstract syntax tree. And you're trying to improve it, trying to make it more specific, a bigger pattern, while keeping all of those original occurrences. So here's an example. If I started with this pattern and it matched 2 places, then my improved pattern might be this. This improved pattern matches exactly the same 2 occurrences, but it's bigger. It has more stuff in it, more non-whole stuff. And, well, how do you do this? Yeah, I guess you could imagine how this is done. It's not rocket science. You know, you say, well, look, there's a particular subtree associated with each hole of the original pattern. And what I'm looking for is a pattern that matches that subtree for all occurrences of this pattern. So you have 2 structures. You have a list of matching patterns for each abstract syntax tree node, so I know what patterns match this node. And for every pattern that matches this node, I know where that pattern matches. So I can just pull it out and say, well, do you match everywhere that I need you to match? And it says yes. And then I say, oh, great. Then I'll fill in this hole with that pattern that matches. I use the biggest one that I can find. So remember, initially we started with just 1 caps, 2 caps, 3 caps. So you have to repeat this process because things are going to fill in sort of as they explore. This, for instance, took probably 2 steps to fill in because it had to fill in the first level and then the second level in order to get to something which is, this is sort of a little bit bumpy. You know, this pattern matches like this, like this.
So the 2 caps of that pattern would be add consub, and then instead of local and const, it'd be question mark, question mark? Yeah.
The 2 caps for this?
Yeah.
The 2 cap would be add, local, question mark, sub, question mark, question mark.
Right, okay, I see. Right, and so if you had started with a 2 cap pattern, you'd find the same kind of end result in some sense, right?
You wouldn't actually have a, so the question was if it matches the same, this is going to be cumbersome, but in anyway, question was, does that, actually that pattern doesn't match. The 2 cap has a local here, and that's a const. And so it wouldn't match. But yeah, in general, you could have started with the 2 cap and and improved a 2-cap. Or even after you've done this improvement, you throw these patterns, these new patterns, back into the pool, and they could be used to improve other patterns. So things get improved in strange ways by this process. You do get this type of a pattern, a lopsided pattern from this type of step. However, there's one thing that's a little bit distressing, which is that I might choose to replace a single hole in the original pattern with a sub-pattern, with another pattern, which has more holes. And so you could see that this could be a bad thing to do, because eventually I would end up with many, many holes, meaning many, many parameters, and not a lot of stuff at the top necessarily. And so you want to kind of limit that. And so there's a threshold on how many holes you can create while you're doing this process. And in fact, sometimes we insist that the number of holes that you introduce by replacing a single hole is the same as the number of holes that you're replacing. So you're only using single hole patterns. You can enforce them. Okay, so far this is just lovely. Except you should be like a little bit suspicious, right? Because this is not going to work, really. I mean, it's not going to do anything good, because I'm insisting that every single occurrence of the original pattern is preserved after improvement. And why? I mean, that prevents you from finding really big clones that occur perhaps only twice. So I need to do something to catch those as well, because I can't grow something beyond a certain level unless it matches every occurrence according to this thing. Okay, so the second part is something that will try to capture that. It's called best pair specialization, and what it does is it says, okay, I only want to keep around 2 occurrences. So what I'll do is I'll look at my patterns, pick up a pattern, look at all of the occurrences of that pattern, and try every pair of occurrences, and then try to find the best pattern for each pair. So this is expensive, you're thinking in your head, and you're right, it is very expensive. So I'm actually sort of lying, but bear with me for a moment. Pick up every pair, and then you grow it. You improve it for just that pair. That's best, and then you take the largest of those. So that means you've improved one pattern by the amount that you can best do to preserve at least 2 occurrences of the pattern. And you throw those back into the pool. And the reason is that's right there. So then, and then you go back to the previous step and you perform pattern improvement again, because now you've enriched the set of patterns and you can do this again. You could imagine doing this multiple times until some sort of fixed point was reached, but actually multiple times in this case really means just 1. You do it again, and then you're done. You don't have to do it once more. Okay.
So the computational complexity of a single cycle of going through the patterns and adding new patterns is what? Is it linear, the number of patterns?
Well, for this step, so the question was computational complexity on this whole thing. This is squared in the number of occurrences of a pattern. That's per pattern. So you're squaring. That's what's going to kill you. That's the thing that's the thing that's objectionable. That's the thing where if I find a pattern that has more than 100 occurrences, I don't want to do this, because that's too expensive. But the actual complexity of doing the improvement step, sort of finding what I should stuff into the holes to make the patterns get bigger, that's all driven by hashing. So it depends on how good your hashing function is. And so you can actually imagine that it's a search, but it's a search for the first pattern that fits all of those holes. So it has a linear running time in terms of, if you believe that hashing works in constant time, you just have to confirm that an occurrence occurs, that a pattern matches all of the occurrences that you have. So it's linear in terms of the number of occurrences. And then if you fail, you have to go to the next pattern that matches and try to see if that pattern matches all of the occurrences. And then you go to the next and to the next and the next. So the number of failures that you perform there, until you reach a cutoff, you actually reach a cutoff point where you say, this type of a pattern is not an acceptable alternative. That is, if it's big, it's expensive to do that stuff. but it all sort of depends on how many patterns match things. So I can't really tell you. I mean, in the worst case, this thing is something like n to the 4th, where n is the number of abstract syntax tree nodes. I'm lying, perhaps, but it's maybe something as bad as n to the 4th. Which brings up, why in the world am I doing this way? I think everyone in the room is already thinking of better ways to do this than the way that I did it. So let me tell you a better way to do this. Well, what appears to be a better way, and then I'll explain why it's not really a better way. So this really is what's being done in the program that I'm going to talk about the results from. Okay, good. This really, what I've just described, is really what's done in the implementation. But I asked Fei to implement this as well, and Fei went off and implemented something different because it was better. So this is what I'm going to talk about next is essentially what Fei told me is better, which turns out.
The machine in our department is too slow to run this one. Do some tricks.
That's because you were programming in Java. Anyway, this is reasonably quick. And anyway, you'll see. But there's a better way to do this, or at least a more efficient way of doing it. So this is called incremental pattern improvement. So incremental pattern improvement is kind of what the name suggests. What we were doing before is we were taking decaps and we were plugging in the biggest pattern that we could find that would match all occurrences. That's when we were doing pattern improvement. We were choosing the biggest pattern that would fit all of the places. This is saying just grow the pattern by one cap at each step. So let me just outline it in the example that we had before, where again we're trying to improve this pattern, the add question mark pattern. What incremental pattern improvement will do is it will do it gradually. So it will find the best one cap to fill in, and in this case it fills in this sub for this hole. Sub matches in both of these cases. And then it'll fill in, then in the next round it'll come back and it'll fill in this question mark with the local. And then the next round it'll fill in this with a B. And then the next round it'll, so it creeps its way down. It's doing it incrementally. And this way I avoid having to keep one of those two data structures that I told you about. I don't have to keep all of the patterns that match a particular node. I don't have to keep that information with the node. All I have to do is keep the one caps that match the node in the tree. And the one caps that match a node in the tree are just basically the node itself. So it's very simple to keep this information. So I'm just creeping down this thing a little bit by little bit. Now, one thing to note here is that we started off with a pattern that had 2 holes in it, and we end up with a pattern that has 2 holes in it. But on the way, we created patterns that have 3 holes. So you have to be a little bit willing to let the number of holes drift. It has to be able to get big in order to get small again. So we'll come back to that in just a minute. There's also a better way to do best pair specialization, because that's what really kills you with the quadratic time. You'd say, okay, well, don't do best pair specialization. That's silly, because what you really want to do is try to improve the pattern by as much as possible, but you do want to improve it. So you want to grow the pattern, but you want to keep as many occurrences as you can. And by doing incremental pattern improvement, you can sort of direct the incremental pattern improvement to choose which improvement preserves the most occurrences. Let me give you another example. It's better. Here's that same pattern, and we want to improve it. We want to specialize it. So what we're going to do is create a new pattern that doesn't match all of the occurrences, but matches as many as we can find. So for every hole, if I improve that hole by, for instance, filling it in with an add operation, so this is the original, these are the original nodes where this occurred, 2, 3, 4, and 5. If I put an add in here, then I only match in position 2 now, because this is the only occurrence that has an add as a left join. Whereas if I put an A in that first hole, there are 3 occurrences where that A occurs. And I can do the same thing for the second hole. It partitions the occurrences into which occur with an add, which occur with a B, which occur with a C. And I can see that of all of these partitions, this is the largest, so I take it. So it's the specialization that I would perform, and it doesn't keep all of the matches, but it keeps most of them. It keeps 3, 4, and 5. And that's called big subset special. You want to pick the big subset of occurrences that occurs most frequently. And then you perform incremental pattern improvement again, and then you sort of repeat the whole process again. So this one you do repeat a couple of times, a few times, to catch everything. Okay, so the pop quiz question, why not do best pair specialization here? If I'm allowing myself to do best pair specialization before, what's worse in this situation than before for this quadratic cost? So there's something that's sort of, well, it's kind of obvious, actually. So probably this is like one of those test questions where you think the answer is harder than it really is, but it's not. The problem here is that when I start with these little 1-cap patterns and 2-cap, when I start with these little 1-cap patterns, the number of matches that I get is humongous. And so I can't afford a quadratic on any of these. I can't afford quadratic best pair specialization on pretty much any one of these patterns. Well, on most of these patterns, let me say. And so I can't do this. I have to do something like this, which is a cheaper alternative, believe it or not, because I don't have to look at every pairwise thing. I can just partition according to holes. So one would think this would be great, and that Fei should be given a medal for coming up with a better way of doing things. And originally I thought, wow, I'm going to just ditch the rest of this stuff and do it. But then when I ran it, I noticed that this is not finding some of the patterns that the other method would find. And the reason is because in order to make this work, in order to make this actually sort of converge on a set of patterns, you have to limit the number of holes that are produced here. You can't let the number of holes grow to 20, for example, because the number of 20 parameter procedures that you can create from an abstract syntax tree is monumental. So what you have to do is you have to limit it. And you're hoping that you limit it by only enough so that you actually can come back to those really good ones like this one that only have 2 parameters in it. But you have to draw the line. And sometimes you draw the line and you've drawn the line too soon. And you miss some patterns that the only way to get to that pattern was to create some 20 parameter thing in the middle that would eventually get scrunched down to a 2 parameter thing or a 1 parameter thing at the end. So that's what was getting missed. So what I'm going to talk about when we talk about results here is the original, the one that I first talked about. But if you're concerned about efficiency, this thing runs in about half the time on a 400,000 lines of Java. This runs in about 5 to 7 minutes, and the other one runs in about 15 to 20 minutes on 400,000 lines, which I think I've done it on bigger things, but I don't remember what the timing is. I remember having to wait for an hour once, and I was shocked. I thought something was bad, but anyway. Okay, so now what we've done is we've detected the clones, and now what we have to do is we have to tell the world about them. So we have to select which clones are interesting. And this is a part where you basically have to perform something that's an art rather than a science. You have to determine what the balance is between size and number of occurrences. And so first of all, let me just say that we throw away stuff that's small, meaning less than 10 nodes from the abstract syntax tree is not really something that's actionable in our minds at the software level. Anything with greater than 5 holes, more than 5 parameters, we also discard that because more than 5 parameter procedures are probably not something you want to create necessarily. Maybe you do. And then you're left to choose how you want to order the clones. An early version of Asta is the name of this system. An early version of Asta, even the current version, allows you to choose sort of how you sort things. You can choose by size, the number of nodes in the abstract syntax tree, which is correlated to the number of tokens or the number of lines and the number of characters in the source. You could order by frequency, by the number of occurrences. So you want the clones that occur most frequently. This would be something that you'd want if you were doing compression, perhaps. You can sort by similarity. You could say, for instance, I'm interested in abstracting procedures that really resemble their occurrences. So I don't want my parameters to be these honking huge things. I want my parameters to be small relative to the size of the procedure body. And if you want that, then you talk about a similarity measure. How similar is the procedure to its occurrence? How similar is the pattern to where it occurs? And so you order them by whatever you want to order them by. So now there's a list of clones ordered by whatever you've chosen. And you commit to them in that order. This is a greedy thing to do. It actually is, of course, NP hard to choose the correct set if you want to optimize. But we do it. You order it and you commit greedily. And you discard clones that overlap the earlier clones, because that's cheating if you say you take this clone and then you've got another clone that you can take as well, because this clone might eat the other clone's lunch. This is what, anyway, so you pick ones, discard overlapping clones, and then you find things like this. So here's an example from Sun's Java 1.4.2. Sun's Java is now probably up to like 5.8.7 or something like that, but whatever. This is an old version, so I'm sure that this is one of the small clones, 59 nodes. It has 10 occurrences. This is within one in the Java directory. And it's a clone that has 3 parameters. See the question mark 1, question mark 2, question mark 3. It has 3 parameters. And it's a reasonable idiom. You would find this a lot. And finding it is not necessarily telling you that it's bad or that it should be abstracted into a function, but it's something that's maybe you'd be interested in knowing what's different between the occurrences that you see. And one of the things, the reason that it's in this slide is because this is an illustration of something that I would call a structural clone. There's a sort of an object field access that's being done here that's not being done here. So this, of course, you could imagine sort of generalizing your notion of what a token is to allow this to be a sort of lexical thing. But things will get more complicated if you do that. And in fact, there are examples of clones we'll see a little bit later that are bigger parameters. But this is just one example. Here's a more local. This is a C# compiler by Hansen and Probstein. I was going to tease Todd about it, but he's not here, so that's too bad. Okay. Well, and too bad. Yeah, that's too bad. So I can just tell you this is some code that he wrote with Dave Hansen here, and this clone is a big clone. It's a 231 node clone. That's pretty big. It's a reasonable number of lines of code, and the only difference between these two is one hole in this big thing, and it's this, which means either one place was fixed or really there's a reason why one is returning a cast to a string and the other one is not. Anyway, I don't know. But these are both examples of structural clones. Structural clones. Here's a bigger clone. This is a bad clone, meaning this is something that somebody was lazy, I believe. They took this original code in which you can see the red things are holes. So in this code, there's a value that's being set that's indexed by I. Here, it's just a constant. And it's getting reset 10 times for whatever reason. I don't know why. But that's the only difference between those two. And so maybe one would want to go in there and fix something to be a little bit more efficient. So.
It has a return and it only says once.
Does it?
It still is a bad example of a code, but it has a return after the set value. So it runs the loop once and then returns.
You're right, except that it runs it 10 times if magic is not equal to text.
Yeah.
So I mean, it's
Yes.
it's probably not what you want. I mean, it just seems like a bad thing to do. Okay, so you can't read this. That's okay. You're supposed to just sort of get an impression. This across the x-axis is individual source files from a Java distribution ordered by size. So the smallest is over there. It's 10,000 somethings. Number of nodes, 10,000 nodes. And here's 44,000 nodes in the abstract syntax tree. And this is a distribution of clones within those files. So as the file size gets larger, you find larger clones. So that's the number of nodes in the clones. There are, for instance, 14 clones of 50 nodes within this thing, within this biggest file of size 44,000 nodes. And it goes up, and you get bigger and bigger clones. And some of them shoot off the charts, but I don't draw those.
Is this clone just within the same file?
Is this clones just within the same file? For this illustration, it is just within the same file.
Okay.
So I'll show you.
Oh, okay.
I'll show you what happens when you look outside.
Okay.
I mean, yeah, very good question. These are all types. So the question was, are these type 1 or type 2 clones? Type 1 clones are clones that are identical. They're lexically equivalent. So there may be white space differences, but they're essentially token stream based. They're the same. Type 2 clones are ones where there's, well, there's a little bit of, I don't know, maybe now there's a standardization as to what type 2 means, but it is standard?
No, it's like widespread. I don't think that you have a standard like IEEE based or something.
Okay, well, let me tell you what type 3 is. Type 3 is essentially you can take anything you want out, interspersed lines of code, remove them, and if what remains matches, that's a type 3 clone. What I'm looking for here, or what this allows you to look for, is type 3 clones. Type 2 clones are somewhere in between type 1 and type 2, and frankly, I know it allows, but it doesn't, contiguous lines, is that the difference? It has to be contiguous lines that are abstracted out?
Parameters,
But it's not only,
types, but no addition of lines, no deletion of lines.
okay, so it's lexical based definition, which says you can have different parameters.
You just rename some variables, you change their types, like change a struct to a class or something, but you don't add or remove anything from the code.
Okay, okay. These are all types. This is just all types of clones that are found by Asta. So it will find type 1, type 2, and type 3. Because it can remove, if you're working in the abstract syntax tree, you end up removing things that are non-contiguous within the source code, and it doesn't conform to the type 2 kinds of clones. And this is the same thing for C#. The file sizes are much smaller. So the largest file here is 37,000 nodes, and this is the distribution on the clone sizes there. So the distributions, basically this is to show you that they grow with the size of the file, and they grow similarly for both Java and C#. So don't think of this as being something that you should find a difference between. It's just that imagine this as being the stuff that occurred before, well, generally speaking, before here. So that's what this is. Okay, so and then this was the question about what happens when you have a global scope versus local scope for your. So if you look at cross-module clones, that's the narrow bar that sticks up a little bit in this graph. This is showing a percentage of nodes that are saved by reducing the program size. You abstract out those functions which represent clones, replacing their occurrences with a function call, and that saves on the number of nodes. And then the y-axis, or the x-axis here, the node threshold is telling you how big you're allowing those clones to be. So if you allow clones to be 10 or bigger, in terms of the number of nodes, then you get a reduction of between 20 and 25 or something like that percentage. And as you increase the node threshold, that decreases the number of possible clones that you allow, but maybe makes them be more actionable, then your percentages go down in this particular fashion. I didn't do a cross module for C#. because at the time I didn't have access legally anymore to the C# compiler because I wasn't here, so I couldn't do it. Bottom line is that this, in terms of reducing program size, this is getting similar results to what is achieved via lexical-based methods and other abstract syntax tree methods, about 12%, and that's what they receive. So we're not beating them in any fashion. But what's weird is that the clones that we're finding are different than those clones. So the clones that Asta finds, they appear to be clones like these clones that I showed before. You know, this is something that you'd want to find, but it's not something that these other things necessarily do find. So this one, for instance, this one down here, is found because it's so large, but this one is never found, which maybe that's, you don't want to find it. But there's another example of one where there are 3 lines in the middle and 2 lines at the end of a big clone, and the 3 lines in the middle and the 2 lines at the end have chopped up this big clone into small enough pieces that neither of the other methods will recognize it as a clone, whereas Asta does. So it's weird. It's a little bit weird. Well, the main question was, you know, what are the relative percentages of structural versus lexical? And here, these charts are showing you based on, again, nodes, the size of the clone, the node threshold. If I'm allowing clones of size 20 or greater, what is the percentage of structural clones of that size? And this, again, is in the Java and the C# source. And then this is saying, what if I allow my node threshold to be varying? So I'm only going to, I'm going to discard clones which have more than a certain number of holes. And if I only allow, for example, 1 parameter clones, this says that about 20% of the 1 parameter clones are structural. They have a parameter that it doesn't just look like a lexical token. You can imagine that this, as you increase the number of holes, you have more possibility of having structural parameters, hence the percentages would increase. You can also imagine that as you look at bigger and bigger clones, the reason why they're bigger might be because they have more parameters, and so they allow more potential for structural clones. So I don't think these graphs are very surprising, but.
I'm not sure I understand the graph on the left. The node threshold.
Oh, sorry. So the graph on the question was about the graph on the left, and the x-axis here is saying only keep clones that are bigger than 20 nodes, or 40 nodes, or 80 nodes, or 160 nodes.
Wouldn't that decrease the number? I'm not sure. So yeah, the intuition is if you only keep ones that are big, then the percentage decreases. So it looks like it's increasing.
No. This is, yeah, the fact that they're bigger means one of 2 things, right? They're either big and they're just full of text, or they're big, they're full of text, and they have many potential parameters that could possibly be filled by structural parameters. The definition of the clone, the definition of whether the clone is structural or lexical is not based on the clone, but it's based on its occurrences. So if a clone has an occurrence which has a structural parameter in it, then it's a structural clone. And so this is giving you, or bigger clones is giving you more of a potential to capture a structural parameter.
The line above the graph is actually it's decreasing the total number of clones.
Oh, the total number. Okay, I get it.
I mean, the
Oh.
percentage is.
Yeah. Okay.
Thanks. Yeah. Thanks. I'm done. Wow. Well, that's not too bad. So in conclusion, their structural clones seem to be forming some significant part, though, you know, you take away from this the question as to, well, what is really structural and what cannot be captured by these other methods, right? So I'm going to have you read the paper in order to see that, because I actually did this competition between all of these other clone detectors. Actually, I didn't do it, but Bellin did it in his thesis. And then I just chimed in at the end and said, this is what Asta finds. And And it's weird because the structural clones that I'm finding with Asta are different than the clones that these other methods are finding, but they're finding things that I'm not finding. And so somehow it's arguing for kind of a hybrid method where you would really want, if you're looking for syntax-based copy-paste clones, you probably want to stick with something that's syntax-based. Whereas if you're looking for clones that are unintentional, not made by necessarily copy-paste programming, but that show up because of idioms that you have in the language that you want to take advantage of by procedural abstraction for comprehension's sake or by procedural abstraction for compaction's sake or whatever, then you might want to look for something that's more structural, more clones that are more structural. So this line is a lot. It is true that it takes less than 1 hour, but it actually takes less than 15 minutes because when I wrote this, I was writing it in, well, I was a little bit, let's just say that I rewrote the implementation and leave it at that. I was a little lazy the first time I did it. So anyway, this is, it's pretty practical, and now, you know, you could work it on 1 million lines of code, and probably it would be around an hour at 1 million lines of code. Yeah.
So when you say 440,000 lines, is that you know, sort of putting the whole 440,000 lines into a single
abstract syntax tree?
Yeah.
Yeah, so what you do is if you have multiple modules, you just hang it from one root.
Okay.
You create one giant abstract syntax tree, and you hand it to the whole thing.
Okay, and it does it against all of it.
And it does it against everything. That's right.
Okay,
Yeah.
cool.
And the future work, I think there's kind of this art section to the talk, which is what's the art of picking the clones that you really want. And it depends on the implementation. It depends on the use. So if you want compaction, you would choose different clones than if you wanted to do software maintenance or software engineering questions. And so there's an interesting sort of work to be done on trying to figure out what's the right thing to do. But I don't know how. You know, there's been a recent paper on sort of the impact of clones on software error, software bugs, and that paper sort of indicates that maybe syntactic-based methods are probably the way to go, and probably that's true. And I would like to see sort of what other benefit we could get from using these structural-based clones in that environment, and also how to use this in a compaction environment. And there's another future work, which is on the reason sort of why I'm here, is you know, abstract syntax trees can be used for the transmission of code as well, and in which case you would like to reduce the size of those abstract syntax trees. And there's methods that come from this kind of subtree finding, pattern matching, that can be used to reduce the size of the abstract syntax tree before applying any other techniques. So that's another thing that I'm interested in. So thanks very much. And I'm happy to take questions if you have any questions.
So, has there been any thought about doing things at the bytecode level?
So the question is, has there been thought about doing things at the bytecode level? There's a lot of stuff. Are you talking about in terms of compression, compaction?
What was clone detection?
Or clone detection? Yeah, the bytecode level, probably most of the research is focused on compaction. So the finding procedures at the bytecode level is sort of like creating instructions that are interpreted by an interpreter. And those instructions, so yes, there has been work done on this, where you basically go through the bytecode and you find essentially common procedures with parameters with holes in the middle. Typically that's based on some sort of grammar for the bytecode that allows you to essentially do a tree type pruning. So you pull out subtrees based on the grammatical structure of the bytecode, and then those become these parameters that get stuck into these. You can think of them as being specially designed instructions that are representative of huge chunks of bytecode. And I'm frantically trying to remember what the percentages are in that for savings, but I think I remember something like 40% savings from from
You can do it
compression.
on x86. I did one on x86 where you were like looking at x86 instructions as like little trees, with little bits of abstraction to them, and it was amazing. Like in a version of Word, I think the 1997 version of Word, there's a factor of 11 in so like the average abstracted instruction in Word 97 occurs 11 times, and you get a total compression ratio of about 40%. So like if you could get to 0.4 of the x86 size by just looking for these little trees and abstracting them, and that was all done at basic block boundaries, so it was still interpretable. You can get more compression if you don't do basic block boundaries, but it's good to do basic block boundaries because then you can decompress incrementally. So the technique works really well at the micro level.
And is there any adoption of it?
Not that I know of. Many people in this room have published papers about these things. Do we know of? Has the world caught on to this?
So my facetious answer to that is bandwidth increased faster than the adoption technique of these techniques.
Yeah.
And so, but having said that, I mean, I think the reality is that binaries are getting bigger too. So the idea of shipping binaries to phones and the bandwidth to phones is still pretty limited. So I think there is just like with power. I mean, even the power issues around transmitting that much code, it drains your battery, right? So I think these issues about performance are coming back, mostly because people aren't just connected to the internet through big pipes now. So.
And I have to say that I got interested in this problem because it's a compression problem with a very code compression is a compression problem with a very objective measure of success. So you can be lossy in compressing code. You can do anything you want in compressing code as long as what you produce still executes the same as the original code. And so there's a goal there for compression that's, it's not like visual compression. It's not like compressing images where you have to sort of say, it looks kind of like the original, and let's measure what looks like means. This is more objective for me. And so a lot of the work that I was doing on code compression was trying to take advantage of the fact that you have this execution going on in the background that can actually decompress code on the fly, if you like, or create an interpreter for you that interprets a large chunk of your program because it happens to be that there's a lot of macro instructions that you can implement for that part. And so
I think you also were observing that one opportunity for deploying more of this technology would be that the ambitions for downloading JavaScript are growing faster than bandwidth.
that's a good way to put it.
So currently bandwidth is growing very gently, but ambition is growing very aggressively. So like SharePoint is downloading millions of bytes of stuff to get going on a SharePoint page, and Office 365 is downloading a lot, and they have a lot of programmers, and so they're generating a lot more to download.
And the original, I mean, the limited memory execution platform, Motivation, kind of goes away every year because the notion of limited memory is like, I mean, how much memory does your cell phone have? It has more memory now than any sort of portable device had 10 years ago. And so, memory is cheap. Transmission, though, is something that's a little bit more problematic.
Cache memory is still pretty good.
That's true. So you can get performance benefits, actually. So what's funny is that you do this procedural abstraction stuff, and then you execute it to show that you haven't ruined performance, and it goes faster.
Yeah.
This actually happens. And at first I thought it was, okay, I'm not measuring things correctly. Something's going wrong. But then I figured out it's the cache. The cache is able to hold more of what's going on. So it does.
We demonstrated, for example, that on Word 97, that you could load Word 97 30% faster compressed than uncompressed. So like your time from double click to the insertion cursor showing up was 30% shorter with the compressed x86 than with the actual x86, because it was just the rate at which the application came up was proportional to the number of disk pages you had to page off the disk. So we definitely have demonstrated, that program compression works. It's probably like a matter of having a killer app that gets you over the software engineering hump. So like at some point there will be a killer app, like say we want to download 10 million lines of JavaScript to run some app, and bandwidth is staying fairly flat. Then at some point someone is going to say, okay, I'm going to get over the hump of software engineering and deploy all this junk. And I'm not sure if there's examples of that yet.
Yeah.
Did you look into, now that you had the ASTs, did you look into any of the semantic properties of the ASTs to think about manipulations on them, like commutivity? And
I thought about it, but if you look at what's been done on that, you don't really save a lot. I can't remember what the percentages were when I was looking at it, but the question was sort of like, if I have a plus operator, it doesn't, something that's commutative, I don't have to worry about the order in which the variables occur, and so I can save perhaps by reordering to make two pieces of code look more similar and save space in that way. But it didn't seem to be a really big win. But it is something that you can do pretty easily with an abstract syntax tree, as long as you know which ones of these operators are commutative and which ones are not. I fear sort of an exponential search cost, so I sort of back away. But it's certainly a very possible thing to do. Yeah.
So you're talking about structural clones being a majority of clones, or?
No. This says it's about 20% of clones.
But that happen a lot.
But
C# and Java.
Oh, sorry. So the question was.
It was on your conclusion slide. So it was the first.
Oh, significant, not a majority, but a significant fraction.
So if we looked at another language like SML or say F#, do you think you'd see that drop when you have? I'm thinking if you have higher order functions, if you have functions that you can pass around a lot of work in there, would you expect to see the structural clones decrease?
Did you say XML?
No, I said SML.
SML.
Yeah, like I
darn,
guess.
I wish you'd said XML, because I could tell you something about XML, but I don't know anything about SML to tell you whether or not it would be more or less prevalent.
You can try to elaborate something, because that really depends on the programmer who we're talking about. Because yes, you have high order functions, you can pass stuff around, and if the programmer uses them as nicely as he should, we won't see as much of the structural clones that we see in the programs like written in Java and C#, because the clones originate, some of the clones originate from this very same problem. They don't have high order functions, and we can abstract something into a function and reuse it, or have a filter function. Like the primitive example, we don't have a filter in Java, and that's why we have millions of clones that do filter. Okay, but if the programmer in SML or F# doesn't use the language wisely, we can see these structural clones, and the big plus with finding structural clones in these languages is that we can actually do something and do something advanced about them. We can refactor them away efficiently by introducing the helper function or something else.
Actually, that is something that I probably should have mentioned, is you can actually, I was talking about parameters that were full subtrees of the abstract syntax tree, but you can imagine having a parameter which is the root of a function. So maybe you're sometimes adding two big things together, and sometimes you're subtracting those two things together. And in some programming languages, you can make that a parameter, so you can pass the function. And then you can create we didn't look at that in what I talked about here, but Fei looked at it in his thesis, his master's thesis. And I don't remember the increased savings when you allow for sort of these internal node patterns, but it was something like 10 to 15 or maybe 15. Anyway, it's been a few years, but you get a little bit of more potential if you have such a language for abstracting the clones. Yeah.
Maybe this is a naive question, but when you make this procedural abstraction, then you are making an overhead of a procedure call. So did you notice that your code slowed down?
Yeah, so as I think I was saying before, it certainly seems like it should slow everything down. And you want to be very careful where you put procedure invocations if procedure invocations are costly. But for one thing, it turns out that they're not so costly. For many programming languages, there's not very much overhead in a procedure call. And for another, you can potentially save because the cache is being used more efficiently. So essentially, you're able to cram more junk that's useful into the cache, and you don't have to page out to external memory as often. So there were actually situations where, after doing this aggressive procedural abstraction, you would get improved running time due to cache effects. I mean, it's not always. In fact, it's sort of, I thought it was an anomaly because it happened on a couple of things, but it does happen.
This is maybe another higher level question that for compaction you have an objective metric that your code size degrees. Is there any such metric for, you can say, if we apply this technique to software maintenance, that do you say that, well, procedural abstraction, so you started with software maintenance, so is there any way to measure that you improved software maintenance?
Well, honestly, only through Herculean efforts could you possibly derive such a measure. Because what you're asking is there a way to say that maintenance is better if I use procedural abstraction for these things? Well, that means you have to stick with a piece of code for long enough to observe maintenance. Mm-hmm. And you also sort of have to present a study in which you didn't do that abstraction versus when you did do that abstraction. This could potentially happen if I could imagine large software projects that you happen to sort of get in at the time when it's forked into two major distributions, and you jump in on one of them and do aggressive procedural abstraction. This has not been done. Nobody has done this. What they have done is they've looked at sort of maintenance records on files that have a high degree of clone in them. And they noticed that there's more maintenance being done on files with more clones. However, that could be because the files are bigger. That could be because their files are, there's so many different variables in this that you really can't tell. However, in some sense, it has to be a win. I mean, there's in some degree having maybe not from the implementation point where you want to write a piece of code, you want to write it quickly. The best thing to do might be for you to just copy it from where it is, plunk it down, and make the changes that you want. So that's a benefit to copy-paste programming, is that you can implement quickly. But how could it be worse to have a procedure in a library or someplace that's doing for you what you want to do versus having to write it again or copy it again? It seems as though, just from the sort of information that you have about the program, that's a better thing. Because now you know, well, where are the places that, for instance, I'm performing the erase operation, where erase is something that erases out some string. It's maybe important for you to understand that erase has to be doing bounds checking, or else, it goes erasing off into wherever. Well, now you have one place to check erase as opposed to having a bazillion. There's, of course, no guarantee that there's not erase functions and a bazillion copies of the erase function lying around called, super erase and all these other things.
So this question was motivated by this fact that if there are different cloning clone detectors in the market and I have to choose the best one of them. Compaction is one thing that, hey, this one gives the most compact
Oh, I
code.
see.
But if I have to look for which improves the maintenance, then you are saying that that kind of study does not exist right now.
No, and so my suggestion for that would be you have to kind of get an idea as to what the, I mean, I'll tell you that most of these clone detection schemes will find big clones that occur in several places. They'll all find them. Like this thing, CC Finder, Brenda Baker's dupe. In fact, I would go with Brenda Baker's dupe because it's been around for a long time. It's easy. It's just run it. It's so simple. But you know, CC Finder has a nice user interface. You know, there's some sort of ease of getting into it, and it finds sort of the big things that are obvious. But if you're looking for, you know, really understanding where you should refactor code, I mean, I would love to, for instance, include this kind of thing into a refactoring engine where you push a button like in Eclipse and say, suggest something to me, because this code is hideous. And it says, well, you may notice that in file 527, there's something that's sort of like that, except that it's got this giant parameter, you know, this giant parameter that's different. You know, that would be great. And it would capture things that perhaps other methods wouldn't capture, or find things that you might consider refactoring that you wouldn't consider via other methods. And so, you know, that would be kind of where I would see this being most useful.
I have a suggestion of one like that. It would be great. The biggest thing that annoys me about clones day to day is if-then-elses where I clone the else case. You know, it's like there's an else of I'm going to do the default behavior, and then there's a sub case. You know, so it's like you've got an outer if,
Yeah.
and then the then body of that has an inner if, and the elses are the same.
Yeah.
So like you must see a lot of that in
Yeah.
your clone detection
Yeah. Yeah.
activities.
Yeah.
I would like a refactoring that would like somehow
Yeah, you'd like a new language, actually.
morph my code around so that that I would only because that else body, A, it's ugly to duplicate it, and B, then it's error prone because then I fix a bug in the else body.
That's right.
And
Yeah.
so is there some, it'd be great if like you just made Eclipse do that one. It would be interesting just to see, could you always make that look better?
Yeah.
Because it's hard for me like manually to make that look better, because the obvious thing to do is use a goto, but I don't want to use a goto because that has its other kind of ugliness.
Yeah.
You know, because like you could, right? You could be like, okay, here's the default action that you take, and I'm going to go to it from all these interior places.
Yeah.
So it would be interesting to see, is there a software refactoring thing that you could do, like detect all those clones and rewrite my control flow so that it looks better?
So, of course, there is, I'm sure, because the refactoring people have been working on all sorts of these different smells and how to fix them. I'm sure there's something out there for doing what you're talking about, but I don't know exactly what it is. And it is something that shows up, though, in these clones. You'll see, it's very interesting to go, I gave you sort of like 3 examples of stuff, but it was very interesting to see the clones that were coming up and say, you know, this is a situation where I'm on the fence between whether I would want it to be changed or not want it to be changed, because if I do change it, then it's kind of ugly and a little bit hard to actually do the procedural abstraction cleanly in some of these cases. And maybe what's resulting is not as nice as what was there before. You know, in your case, I think it'd be pretty clear-cut. Sort of, yeah, it's like I should do it, but sometimes it was sort of a on-the-fence issue for me.
Well, it's hard. Like sometimes it's hard because, like a good example is you're writing type checking code, and you are trying to figure out whether one type can be cast to another type.
Yeah.
So you go down this like long chain of if-then-elses, like, well, if the left type is the null type, and the right type is a reference type, then I can switch it around and do this. But if the reference type is not subtypable by the other, you know, and you get the stuff, and then all the else's are, you know, report error incompatible types, and then like little trees on what the incompatible type is, right? You see what I mean? That are slightly different.
Right. Well, they do. Yeah. So you know that I'm not a software engineer, and you know that like I know very little about anything about anything, but you know there are constructs and other languages that basically are supposed to be handling those cases. in kind of a unifying way. So they, you know, you throw exceptions or you do something or you do whatever, and then you collect all of these things in one place and you do all of your,
So like a structured go-to.
yeah, like a structured go-to,
Because
basically. That's right.
Because
Which
like
is
basically you're removing that case down to, I identified that case, and
Yeah.
then you handle that case somewhere else.
That's right. And
Yeah, so I could do that. Like I could number my cases, and then I could have a case handler.
And basically, you want like an advanced pattern matching that most functional languages have, like Erlang, like Sharp, like Scala. So you want this match, like two types with the left type is this, right type is this, blah 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 blah. Default stuff with row and error.
Yeah, I see. You mean so like instead of having nested if then else's, you would have a flattened pattern matching statement, like a structural type case.
Much better to maintain and to add some new cases to it.
That's a good point. That's
But you can't have in like most mainstream languages.
yeah, but like I have my choice right now is JavaScript, which doesn't have goto either, so I can't actually. But yeah, that's a good idea. The structural pattern matching.
you have to write a pattern matcher now.
Yeah, well,
You can add it to your.
we can add it to our syntactic
Exactly.
sugars on JavaScript.
Well, thank you again. Thanks very much.